It's time for Math with Mr. Young. Lesson 100, Estimating Square Roots and Irrational Numbers. Let's begin with a power-up. You can use the worksheet provided, or simply pause the video and use a blank sheet of notebook paper to answer the problems on your screen. Go ahead and pause now, and resume once you've completed all of the problems in this power-up. Okay, today's power-up reviews balanced equations with a variable. Before we dive into the answers, I want to point something out which might help you to remember how to solve these kinds of equations that have a variable in them. Let me start with this problem, which is a lot like an order of operations problem from your last lesson's power-up. 2 times 3 plus 1. If we were to solve this, we would first do the multiplication. 2 times 3 is 6. Then we would add the 1. And our answer is 7. But what if, instead of starting with all of this information on the left and looking for what goes on the right side of the equal sign, what if instead the problem gave us what goes on the right side of the equal sign and took away one of the numbers on the left side? So now we have 2 times question mark plus 1 equals 7. Of course, we already know the answer. But if we didn't know it, what would we do? Well, we know that when we worked left to right, we followed the order of operations. But when we already have the answer over here, and we need to work backward to find one of the pieces over here, we need to work backward through the order of operations. So what's the last thing we did when we first solved the problem? We added 1. So now let's undo that step. How do you undo addition? You subtract. So subtract 1 from both sides. Plus 1 and minus 1 cancel, which is what we wanted. Then 7 minus 1 is 6. So now we're left with 2 times something equals 6. What was the step we did before the addition in our original problem? That's right, multiplication. So now we undo the multiplication. So we divide by 2. If we have 2 of something and then we divide by 2, what are we left with? Just 1 of that something. When we divide 6 by 2, we get 3. So now we're left with something equals 3. That's the correct answer, remember? This is the process we are doing in our power-up. Luckily for us, the power-up reminds us which steps we are supposed to do first. But now you know why. When we're trying to find the value of a variable within a problem that we know the answer to, we move backward through the order of operations to find it. So let's try number 1. 2x plus 5 equals 45. Remember, if we knew all the numbers on the left and we're trying to find the answer over here on the right, we'd follow the order of operations. But now we're looking to find the value of this number here in the middle of the problem. So we have to work backward. The two operations in this problem are multiplication and addition. Normally, multiplication would come first and addition second. But since we are working backward, we're going to undo the addition part first. To undo addition, we subtract. Subtracting 5 from this side cancels out the 5. Subtracting 5 from this side leaves 40. Now we're left with 2x equals 40, which is the first answer our power-up asked for. Now we undo the multiplication. To undo multiplication, we divide. Dividing 2 times x by 2 leaves us with just x. The 2's cancel out. On this side, 40 divided by 2 leaves us with 20. So x equals 20. And that's the second part of our answer. Next up is 3y plus 4 equals 22. This problem looks very similar to the last one. So let's remember the steps. First, we undo the addition part. Subtracting 4 from this side cancels the 4. Subtracting 4 from this side leaves us with 18. There's the first part of our answer. Next, we undo multiplication. Dividing 3y by 3 leaves us with just y. Dividing 18 by 3 leaves us with 6. So we have y equals 6. That's the answer. The next one is 5n minus 3 equals 12. The primary difference with this problem is that it has subtraction here rather than addition. So how do we undo subtraction? We use addition. When we add 3 to this side, we have 5n minus 3 plus 3. The minus 3 and plus 3 cancel out. When we add 3 to this side, we get 15. 5n equals 15 is the first part of our answer. Now we undo the multiplication. To undo 5 times n, we divide by 5. On this side, the 5's cancel. On the other side, 15 divided by 5 is 3. Now we're left with n equals 3. And we're done. 3m minus 7 equals 14. Once again, this problem looks very similar to the last one. So let's do the same thing we did before. Undo the subtraction part by adding 7. 3m minus 7 plus 7 just leaves 3m. 14 plus 7 equals 21. That leaves us with 3m equals 21, the first part of our answer. Now we undo the 3 times m by dividing both sides by 3. 3m divided by 3 leaves m. 21 divided by 3 leaves 7. m equals 7 is our answer. 15 equals 3a minus 6. This problem looks a little bit different than the last one. Last time, we had one number on the right, and it looked something like this here on the left. Don't let this trick you. If you're worried it might trick you, you can go ahead and rewrite the problem the way you're used to, putting the single number over here on the right. Why can we do that? Well, think of it this way. If I tell you that I have something in my hand here, and then I tell you that I have something in this hand too, and that it's the same thing that's in my other hand, then you know that what's in here is equal to what's in here. Does anything change if I switch my hands to the opposite side? No, they're still equal. So let's go ahead and do that for this problem. Switch the sides of the equation, and we'll solve like this. First, let's undo the minus 6 by adding 6 to both sides. The 6's cancel here, and 15 plus 6 equals 21. 3a equals 21 is the first part of our answer. But you'll write it the other way around on your power-up. 21 equals 3a, which is the same thing. Now, let's undo the multiplication here. 3a divided by 3 is a. 21 divided by 3 is 7. Now we have a equals 7. Once again, your power-up will want you to write it the other way around. 7 equals a. 24 equals 2w plus 6. Once again, this problem is written differently than we're used to. But let's try to solve it this way anyway. The steps are the same. First, let's undo the addition operation by subtracting 6 from both sides. After we cancel the 6's on this side and subtract 6 from 24 on the other side, we're left with 18 equals 2 times w. That's the first part of our answer. Next, we undo the multiplication operation by dividing both sides by 2. 2w divided by 2 is w. 18 divided by 2 is 9. So we're left with 9 equals w. There, that wasn't so bad, was it? Next up, we have negative 2x plus 9 equals 23. The new idea this brings to the table is the negative sign here. But don't let it throw you. Follow the same steps. First, let's undo the addition operation. We subtract 9 from both sides, leaving negative 2x on one side and 14 on the other side. That's part 1. Next, we undo the multiplication operation with division. Can you guess what we divide both sides by? Well, when we had 2x in our very first power-up problem, we divided by 2. Here, when we have negative 2x, we divide by negative 2. Once again, x times negative 2 divided by negative 2 lets us cancel out those negative 2's, leaving us with x. On the other side, we divide 14 by negative 2. Remember the rule for multiplying and dividing negatives. If the two numbers have the same sign, the result is positive. If the two numbers have different signs, the result is negative. 14 and negative 2 have opposite signs, therefore the answer will be negative. 14 divided by negative 2 is negative 7. And there's our answer. X equals negative 7. Next problem. 20 minus 3y equals 2. This problem can seem very tricky when you first look at it. But I want you to notice something. How does this problem compare with the previous one we just completed? The problem is actually very similar. Remember, whenever you add two things together, you can switch them around no problem. That's the commutative property, which is a property of addition. 2 plus 3 is the same as 3 plus 2. So if we take the numbers in our previous problem, negative 2x plus 9, we could have switched them around. 9 plus negative 2x. Here's our new problem. Now do you see the similarity? What if we change the 9 plus negative 2x to 9 minus 2x? That means the same thing, doesn't it? Now the two problems look very similar. So let's think about our new problem. What if, instead of writing it as 20 minus 3y, we wrote it as 20 plus negative 3y? Then the 20 and the negative 3y can switch sides using that commutative property. And we're ready to begin the problem. Don't forget that the commutative property only works with addition. You can't switch around the numbers while the operation is subtraction. 3 minus 2 is not the same thing as 2 minus 3. Very different. But if you change the 3 minus 2 to 3 plus negative 2, then when the numbers switch sides, it still works. Okay, back to the problem. Negative 3y plus 20 equals 2. Undo the addition operation by subtracting 20 from both sides. The 20's cancel, and 2 minus 20 is negative 18. Next, undo the multiplication operation by dividing both sides by negative 3. This side cancels everything except y. The other side has negative 18 divided by negative 3. Since both numbers are negative, they have the same sign, the result will be positive. Negative 18 divided by negative 3 is positive 6. We're finished. 1/2 m plus 6 equals 18. First step, undo the addition. Subtract 6 from both sides. Now we have 1/2 times m equals 12. Now we have to undo the multiplication. To do this, we must divide both sides by 1/2. But before we try to go ahead and divide both sides by 1/2, let's remember something about dividing by fractions. If I have a fraction divided by a fraction, I can change the division sign to multiplication if I flip the fraction which follows the division sign upside down. And if you think about it, this makes sense. If I take 1 whole and divide it in 2, I'm left with half. Both of these numbers can be written as fractions. Now apply the method I said before. Change the division sign to multiplication, remembering to flip over the fraction that came after the sign. Now I have that 1 whole, but instead of dividing by 2, I'm multiplying by 1/2. 1/2 of the whole is 1/2. See how that works? Dividing by 2 is the same as multiplying by 1/2. So in our problem up here, we're dividing by 1/2. But we can change the division into multiplication if we flip the fraction on this side of the division sign. So we discovered that dividing by 1/2 is the same as multiplying by 2. So let's do that to both sides of the equation. That's going to be much easier. 2 times 1/2 times m equals just m. 12 times 2 is 24. And there's our answer. 3/4 n minus 12 equals 12. First step, undo the subtraction by adding 12 to both sides. These 12s cancel on this side, and these 12s add together to become 24 on the other side. That's the first part of our answer. Now we must divide both sides by 3/4. We remember from the last problem that dividing by 3/4 is the same as multiplying by 4/3. So we go ahead and do that to both sides. Over here, 4/3 and 3/4 cancel each other out. On the other side, 24 times 4/3 is 96 over 3, which reduces to 32. And there's our answer. 3y plus 1.5 equals 6. First, undo the addition part by subtracting 1.5 from both sides. That leaves us with 3y equals 4.5. Now, divide both sides by 3. And there's our answer. Y equals 1.5. Finally, 0.5w minus 1.5 equals 4.5. First, undo the subtraction by adding 1.5 to both sides. That leaves us with 0.5w equals 6. Now, divide by 0.5 on both sides. This side cancels out. Now, when you divide by a decimal, you can make it simpler by moving the decimal point over in both the dividend and the divisor. 6 divided by 0.5 is the same as 60 divided by 5. So your answer is 12. W equals 12. We're all done. Here are the answers to your power-up once again. Feel free to pause the video and rework any answers you got wrong. Okay, pull out your notes page. The first thing I want us to do is remember perfect squares. A perfect square is a number which, when you take the square root of it, the result is an integer. 9, for instance, is a perfect square, because the square root of 9 is 3. Let's go ahead and make a list of some of the common perfect squares you are likely to see in your math work. 1 times 1 equals 1. So 1 is a perfect square. 2 times 2 equals 4. So 4 is also a perfect square. We already mentioned 3 times 3. And we can keep going like this. Let's go all the way up to 13 times 13. It's a good idea to be familiar with all of these perfect squares. We will use our perfect squares in order to estimate the value of the square root of squares that are not perfect. How do we do that? Well, the best way to show you is with an example. let's estimate the square root of 46. To do this, we first should notice that the number 46 is larger than 36 and smaller than 49. What does this tell us? It tells us that the square root of 46 must be between 6, the square root of 36, and 7, the square root of 49. And since 46 is much closer to 49 than to 36, we should expect that the answer will be a little bit closer to 7 than to 6. Let's draw this on a number line. Here is a point for the square root of 36, or 6. Here is a point for the square root of 49, or 7. If we were to plot the square root of 46 on this number line, we'd put it somewhere around here. If we want to refine our estimate, here's how we can do so. Think of all the possible values for the tenths digit between 6 and 7. There's 6.1, 6.2, 6.3, and on and on. Now, based on the position of the point on your number line, pick which one of those numbers you think is the best estimate of the square root of 46. I'll start with 6.6. So, find the exact value of 6.6 squared. 6.6 squared is 6.6 times 6.6. So our answer is 43.56. That number is less than 46. So let's try 6.7 next. 6.7 squared is 6.7 times 6.7. That equals 44.89. That answer is also less than 46. So let's do this again and try 6.8. 6.8 squared is 46.24. That number is larger than 46. So now we know that 6.7 squared is less than 46, while 6.8 squared is more than 46. That means that the square root of 46 must be somewhere between 6.7 and 6.8. And since 46 is closer to 46.24 than it is to 44.89, we can guess that our answer will be closer to 6.8 than to 6.7. So we now have an estimate of 6.8. If we wanted to, we could refine our answer even further. We could put 6.7 and 6.8 on a number line and take a guess as to where on that number line our square root of 46 would fall. I'd guess somewhere around here. You don't have to do this next part with me, just watch how it works the same way. I'll put hash marks in between here and follow the same steps that we did before. First, I'll guess at the answer. Maybe something like 6.78 to start. 6.78 times 6.78 is 45.9684. That is less than 46. So now I'll try 6.79. 6.79 times 6.79 is 46.1041. That number is larger than 46. So now we know that the square root of 46 is between 6.78 and 6.79. And since 46 is closer to 45.9684 than to 46.1041, 6.78 would be my estimate. If you had all the time in the world, you could keep going like this, refining your answer on and on, getting ever closer to the true value of the square root of 46. However, you'd never actually finish estimating. At no point will you ever find a number that is exactly equal to the square root of 46. That's because the number is irrational. If you've forgotten about irrational numbers, go back over lesson 86 in your textbook. Irrational numbers cannot be expressed as either a decimal or a fraction. So if we want our answer to be exact, we must leave it as the square root of 46. Otherwise, we estimate to whatever decimal place the problem asks of us. Here's another example. On this triangle, find the length of side C. Estimate the length to one decimal place. To solve, we must remember the formula from our previous lesson. A squared plus B squared equals C squared. Let's plug in the information we know. A is 4 feet. B is 5 feet. And we're looking for C, so we leave that as a variable. 4 squared is 16. 5 squared is 25. 16 plus 25 is 41. Take the square root of both sides, and we find that our answer is the square root of 41 feet. Let's use our notes page to help estimate the value of the square root of 41. Find the largest perfect square that is smaller than 41 and the smallest perfect square that is larger than 41. Here they are. 41 is between 36 and 49. Let's draw our number line. On this side, put the square root of 36. On this side, put the square root of 49. Let's put our hash marks underneath and then estimate where on this line our answer should go. 41 is a little bit closer to 36 than to 49, so let's put the square root of 41 right about here at 6.4. Now, let's square 6.4. 6.4 times 6.4 is 40.96. That's a tiny bit too small. So now let's square 6.5. 6.5 times 6.5 is 42.25. That is too big. So now we know that our answer must be between 6.4 and 6.5. But we also know that because 41 is much closer to 40.96 than to 42.25, that 6.4 is our best estimate. So there's our answer. The length of side C is approximately 6.4 feet. Well done. Now it's time to open your textbook. To complete this lesson, start by doing the example problems provided. Try to solve them on your own before you look at the solution and the steps. Once you think you have the correct answer, check your work by walking through the steps, making sure that you arrived at the solution the correct way. Once you are done, you're ready to move on to your homework. See you next time!